And we're at the next talk for meeting C++ 2025. Right now, we will listen to Erik Tomusk about does my C++ object model work with a GPU, which is a really interesting topic. Looking forward to your talk. Please take it away, Erik.
All right. Welcome all, and thank you for tuning in. I'll be sharing some information about the C++ object model and GPUs. So let's get this started. Before I get to the interesting stuff, here's a brief introductory slide about me. This isn't really important. The important part of this slide is this disclaimer. This is very much a personal presentation. So all of the opinions here are my opinions rather than necessarily anyone else's. Also, it's important to remember that this presentation isn't meant to be implementation advice. So I don't know the problem that you're working on, so I can't suggest how you should solve it. There might be ideas in this presentation that are helpful to you, but please always do your own homework before committing to a technical solution. So with that out of the way, let's get to the more interesting stuff. What I've done is I've put together 4 topics that I want to talk through. And the first of these is C++, and specifically the C++ object model. Now, this is a very big topic, but this is also a topic that I expect this audience to be quite familiar with. So my goal here isn't really to present any new information. What I'd like to do is touch on a few key ideas that we should all be familiar with, but that this will be the foundation for some of the things that I share later. So to do this, what I've done is I've put together a textbook conversion of C code into C++ code. So I've got the C code here. I declare a data struct, and then in the usage below, I'm allocating memory for this data struct. I assign that to a variable, then I set a data member, and then when I'm done with the struct, I free the memory. So there are a number of ways of converting this code to C++, and one of them is the one I'm showing here, where I've kept the data struct as is, but I've written a C++ wrapper class around it. And now the memory allocation is done in the constructor of the wrapper class there, and the deallocation happens in the destructor, and we've got a private data member that points to the actual struct. And then the usage of this class is on the far right, where I create an object of this class and I call some data member, so some member function. So this is fairly straightforward. So this is kind of base level C++ stuff, and this should be quite obvious. But there are some really important ideas as far as C++ goes, just in this small bit of code. So there's a few things I want to call out here. The first is that this is an example of RAII, resource acquisition is initialization. And in this case, what this means is that by constructing an object of the type my class, I'm initializing that object to a reasonable state. And for this particular class, this means allocating memory for the data member, which is the pointer to the struct. This code is also an example of encapsulation. That means that the wrapper class owns and encapsulates a different object, and the user of the wrapper class has no idea that that object is there. This code is an example of automatic storage duration. So you can see that in the usage example, I have an anonymous scope where the object lives. And once that scope finishes, that object is destroyed with the help of the object's destructor. And kind of more broadly, then this code shows the idea of ownership, where my wrapper class has ownership of a separate object, the struct. And that means that the wrapper class is responsible for creating the struct, keeping it in a reasonable state if that's what's needed, and then cleaning up after it when the wrapper class itself is destroyed. And also, in a way, the anonymous scope owns the Chris object. And that means that when the scope finishes, the Chris object that it owns also goes out of scope and gets destroyed. So these are all fairly straightforward ideas. We should all be familiar with these. There's a common theme running through them, and that theme is local reasoning. All of these ideas exist to help us as software developers reason locally about the problems that we're solving. So we're able to avoid peripheral unrelated details and lower level details, and all that complexity, and focus on the problem we want to solve. And that has a side effect of helping us avoid some bugs as well. So next, I want to talk a little bit about how interfaces factor in with local reasoning. The class I just showed you, there are many ways of implementing this class to have the same interface. And the user of the class shouldn't need to know or care about the implementation. It's up to the class how it manages any objects and any other state that it owns. So the classic example of this is that a class might store objects internally or keep them in a separate heap allocation. And I'm showing that with these three possible implementations of this class, where the implementations are the same except for this private data member, which might be a pointer on the left or a value in the middle or an optional value on the right. But then this is important for local reasoning because the user of the class is able to reason locally because they're only talking to the class interface. And the implementer of the class is able to reason locally because they're only looking at the implementation without having to care about what the user is doing. Now, it's helpful to think about what makes local reasoning possible. And one of the considerations is the memory hierarchy. I think most people in this audience will have seen this diagram before. We all know that a modern CPU has a memory hierarchy, so various levels of cache, which are ultimately backed by DRAM and potentially also a swap file on disk. And the CPU, combined with the operating system, go through a whole lot of trouble and a whole lot of complexity to provide our applications with an illusion of a large flat address space that our applications can use. And this applies to C++ applications and other applications written in other languages as well. And then, pulling this back to interfaces, the user of a class is concerned with the interface, not the implementation. The implementation of a class is able to do all sorts of things to provide the interface. And those things might involve using lots of memory or less memory or changing the amount of memory that's required. But basically, the user of a class doesn't really know or care about the amount of memory that a class is using. So the memory hierarchy and the virtualized memory space, it gives classes kind of a space to expand into in an effort for those classes to provide their interfaces. Obviously, memory hierarchies have performance implications, but they don't affect correctness. And yes, I know this is a gross oversimplification. But it's worth thinking about why we actually care about these things, interfaces and local reasoning and so on. And the first part of this answer is code reuse. If we write our C++ classes with reasonable interfaces and write them to be well-defined and well-behaved C++ classes, that means we can use them with existing C++ code. So for example, if I write a class, I can stick it in a std vector. The broader version of this answer is libraries and code reuse through libraries. So I'm showing an application stack diagram here. And all of these libraries will have some sort of interface and some sort of implementation that's somewhat decoupled. And all of these libraries can be implemented in a number of different ways. The point of interfaces is that the application doesn't need to know how much, for example, memory library 1 is using. The application might not even know that library 1 is there. And this is possible because of interfaces, because the developers of these libraries are able to reason locally, and because the library 1 has a lot of memory potentially available to it that it can expand into to do what it needs to do without worrying the application about that. And alternatively, if the application had to allocate memory for library 1, we would lose all sorts of encapsulation, and that would make our application very difficult to develop. And then the third part of local reasoning is productivity. It gives us less boilerplate, which helps us with being productive, writing fewer bugs, and so on. So next up, I want to take this a step further and look at class invariance in C++. An invariant is a set of conditions that is guaranteed to always be true for valid objects. So the way C++ goes about this is the constructor of the class constructor establishes the invariant. the member functions of an object preserve the invariant, and then the destructor destroys the object and its invariant. And I've got an example of this on the slide here. So on the left, I've got some code that assigns some hexadecimal value to a data member of some object. When we look at this code, it's not at all clear whether this value is a valid value for this data member. And it's also not clear whether assigning this value to this data member leaves the object into a reasonable state, because the object might have other member values that have different values, and those values collectively don't make sense anymore. So the point of this is that for this object with this interface, the object's internal consistency is actually the responsibility of the user of the object. So we don't have encapsulation anymore. Whereas the code on the right, the object has a member function. We call that member function to set some flag. And at this point, the object's internal consistency is the responsibility of the object and its member functions. So we have the potential of having a reasonable invariant. So to flesh this out a little bit more, I put together a more complicated example. So here I've got a function that takes a std vector, a reference to a std vector as a parameter, and I call a whole bunch of member functions on that vector. And the thing to note about these member functions is that they all preserve the vector's invariant. And that means that I can do the following. I can rearrange these function calls, and this is still a valid function. So calling the member functions of the vector in a different order is still a correct usage of that vector. Obviously, calling them member functions in a different order makes my function do something different. But both arrangements are correct as far as the vector is concerned. But it's worth noting that only one of these arrangements can be correct as far as my function is concerned. So this helps us see the value of invariance, but also the limit of invariance, where, and the way I like to put this, and this is borrowed from Sean Parent, is that correctness is not composable. I can use a vector in a correct way, but that doesn't mean that my code will do what I want it to do. It will do something that's correct with respect to the vector, but it might not do something that's correct with respect to my intent. All right, so let's summarize the key ideas from the C++ object model section. And the overarching idea I want you to take away from this is local reasoning. C++ has local reasoning that is supported by invariance, RAII, encapsulation, ownership, automatic storage duration, all of these ideas. Local reasoning supports productivity, correctness. It helps us focus on the problem and not peripheral or low-level details. And local reasoning greatly benefits from the illusion of a very large virtualized address space that the hardware and the operating system create. Obviously, local reasoning is possible without a virtual address space and without a memory hierarchy, but the virtualized address space and memory hierarchy greatly help us separate the concerns and help us have interfaces and implementations that are somewhat decoupled from that. Okay, so that was the C++ object model. Next up, let's look at OpenCL and a little bit of Vulkan. So the topic here is accelerated compute. When we think about accelerated compute, the paradigm we have in mind tends to be one of offloading. So that's what I'm showing in this diagram, where we have a software stack of an application and some libraries executing on a CPU, and there's an accelerator off to the side. And then some special functions in the software stack get handed off to be executed by the accelerator, and usually this happens asynchronously. These special functions are called kernels or shaders, depending on the API that you're using. And this has nothing to do with operating system kernels like the Linux kernel. It's a different use of the same word. When we talk about accelerated compute, in this context, the word compute usually means doing a whole lot of math in parallel very quickly. Accelerators do this much faster than CPUs, which is why we want to use them. And it's worth noting that some applications need so much compute that the application spends most of its time just handing off work to accelerators and waiting it to come back. At the moment, GPUs seem to be the most commonly used accelerator, but there are accelerators other than GPUs out there. But because GPUs are so common, I sometimes use GPU and accelerator interchangeably. Also, we all know GPUs are used for more than graphics. Then OpenCL is a compute API, so I'll focus on this section on that. But I'll also mention a little bit about Vulkan, which is a graphics API, but it supports compute. Now I'll briefly go over some accelerated compute vocabulary. When we talk about a device, this usually refers to a physical accelerator device, like a GPU, but it can also refer to a software abstraction of that device. When we talk about the host, this refers to the CPU. When we talk about kernels and shaders, these are special functions that execute on the accelerator device. When we talk about buffers and images, these are ways of storing data for the accelerator to use. A command is an action that an accelerator performs, usually asynchronously, and this includes things like executing a kernel or copying data. And when we talk about a queue, a command queue, or a command buffer, these are software abstractions that are used to schedule commands to a device for asynchronous execution. All right, so next I'll give a brief overview of OpenCL, just so you get an idea of what accelerator programming actually looks like. OpenCL is the Open Computing Language. It's a C API that's developed by the Kronos Group, and it's supported on a number of different accelerators. What I've done is I've put together a minimal OpenCL example. I have omitted a lot of the boilerplate and code and details, so this isn't a complete program, but this is just to give you a sense of what's going on. And the code is here. So in an OpenCL application, often quite early on, we create what's called a CL program. And this is kind of, the word is it's a weird use of the word, because a CL program isn't actually a program. It's kind of like a library of kernels. This CL program is created with the help of an OpenCL context, which is just a different struct that I haven't shown the creation of this, but it's there. And often there's a source string involved, because OpenCL applications, they will often embed their kernels in raw source form in the application, and then during the execution of the application, the kernel code is compiled into an executable form. And that's what happens here. So we have some just-in-time compilation. Here I create an input buffer and an output buffer for my kernel. The kernel is created here. The kernel is kind of like a function, so I need to set its parameters, and that's what happens with this setKernelArg function call here. Here I create a command queue for executing the kernels on the accelerator. I enqueue a data copy. So this copies the input data from the host to the accelerator device. Then I enqueue the execution of the kernel, and then I enqueue a copy back to the host. And then I wait for all of this to be done. And then there are a bunch of these release functions that release the resources that I've created. So there are a number of observations about this code that I'd like to call out. And the first of these is, if we look at this setKernelArguments function, and if we imagine calling the setKernelArguments function later on in the code, what you can see is that by rearranging the code like this, I've submitted a kernel for execution before I've actually set one of its arguments. And this shows that OpenCL doesn't really have this idea of invariance. It's easy to create a partially initialized object, and it's easy to use an invalid object. The second observation I want to make is that there's no RAII here. So here, if we look at this kernel object, when the kernel object is created, it's only partially initialized. So the kernel object, it needs arguments. It doesn't know what the arguments are yet. And we have a lot of explicit cleanup code that the API user needs to do. And the user needs to remember to release these objects. And this means that OpenCL objects are essentially global state, which makes it very difficult to track who owns a particular object and who has responsibility for freeing it. Also, OpenCL objects don't obey scoping rules, so it's easy to write leaks, where you lose all references to an object, but it still somehow exists. And the third observation I'd like to make is that memory is no longer the only resource. And this is a little bit more involved. So if you look at this code, you can see that OpenCL has many different types of resources. So it's got devices, contexts, buffers, images, queues, and so on. And some of these resources can have hard upper bounds. So for an example, every OpenCL queue could be backed by a physical queue circuit on an accelerator. And that means that in your OpenCL program, you can only create as many queues as the accelerator physically supports. That means that creating these OpenCL resources is a lot more complicated than just allocating host memory in a normal program that executes on your host. There's no equivalent of the memory hierarchy when it comes to these OpenCL resources. And that means that if you have a large application where lots of different functions and libraries are allocating resources, it's easy to potentially run out of these. So the point of all these observations is that writing OpenCL, we don't really get any of the benefits of the C++ object model. So the question that come to mind looking at this, and this is certainly that I came up something I came up against when I first started seeing this type of code is, oh, why is this so complicated? Can't I just get a function that will run a thing on a GPU and it will do it for me? And there's really a good reason why this is so complicated. Most of these accelerator APIs are deliberately designed as explicit resource management APIs. And this includes things like OpenCL and Vulkan. And the reason for this is that you need to be able to manage resources explicitly to be able to do optimizations that are critical for performance. And remember, we're doing accelerated compute because we want good performance. And examples of this are things like you can copy data to an accelerator while executing an unrelated kernel. You can copy data to an accelerator once and run several kernels on it. Well, and for some accelerators, you can potentially run 2 kernels at once. So when it comes to accelerator APIs, explicit resource management is a feature. It's not a bug, but it does make accelerator programming really, really difficult. So an immediate follow-up question when looking at this, and again, something I've wondered myself, is can't we just create C++ wrapper classes around our accelerator objects and get the benefit of the C++ object model? So remember, I showed you an example of taking some C code and putting the memory allocation in a constructor and the memory deallocation in a destructor. Can't we do the same thing with OpenCL? So we have a class and we create a buffer. So we have a buffer wrapper class. We create the actual OpenCL buffer in the constructor and release it in the destructor. And the answer is, well, kind of, sort of, you can do it. C++ headers exist for OpenCL and Vulkan to do exactly this. It can potentially simplify some things, but the underlying problem is really a lot more complicated. So we don't really get nearly as much mileage out of this approach as you might initially expect. And the way I think about this is, if you imagine a dependency graph for the OpenCL objects that are needed to execute just one kernel, and I've gone ahead and drawn out this dependency graph. So if I want to execute an OpenCL kernel, what I need is to create an OpenCL command queue and an OpenCL kernel to execute on that queue. To create the kernel, I need some memory objects, so that's probably buffers, and a program that kernel comes from. To do those things, I need an OpenCL context. Before I can have a context, I need a device ID. The command queue also needs to know about the context and the device ID. And before I can get started with anything, I need a platform ID. So if you look at this complicated web of objects and their dependencies, what we would like to do if we want the C++ object model is to provide a C++ abstraction on top of this that has some sense of good class invariance to help us avoid bugs, and a clear view of ownership so that we don't leak resources and we don't have dangling references. And this would allow us to write accelerator code easily from C++, and it would allow us to make accelerators usable in a way that's useful to C++ developers. So we can think about what the abstractions might look like that we layer on top of this complex web of objects. And at one extreme, we could just try to wrap all of OpenCL inside a C++ class. And this class would then create all the necessary OpenCL resources that we need. It would execute our kernel for us, and then it would free all of those resources. And then the user would need just one class to deal with. So in some sense, this is a potentially nice solution. We have some sort of invariant, and it's fairly straightforward what that would be. We have a clear view of ownership. All of the OpenCL resources are just owned by the C++ class. We have RAII. But this is horribly inefficient. Every time you use this class, you need to create a whole bunch of things and then destroy them later. So that there's a whole lot of repeat work. And this is basically impossible to optimize, because optimization sometimes relies on the accelerator doing more than one thing at once. There's no way to do more than one thing at once with this. So this solution is only really good for applications that only ever need to execute one kernel and to do it once. So we can think about another extreme solution at the opposite end of the extreme. And I've already referred to this a bit. We can imagine taking all of our OpenCL types and wrapping them in each in a C++ class. And this would allow us to write essentially the same OpenCL code that we did before, but with some C++ niceties. And this is comparable to the official OpenCL C++ headers that are available. So we have the same optimization opportunities as OpenCL, so we can potentially get good performance. But it becomes very difficult to define useful invariants. So remember, I pointed out that it's only valid to enqueue a kernel for execution if you first set its arguments, but also if you first actually copied that data to the accelerator. So what the C++ level of C++ level invariant for an OpenCL kernel looks like, it's quite difficult to pin down. There's no clear view of ownership. So for example, if you have an OpenCL context and an OpenCL buffer that lives in that context, if that context is destroyed, that buffer suddenly becomes invalid. And which means we're back to the problem of resource leaks and dangling references. And then there's the question of RAII. This kind of C++ abstraction does have RAII. It can work. But without a clear view of ownership, this becomes a foot gun, because RAII is all about automatically releasing resources. If a context gets automatically released while a buffer that the context depends on is still alive, then that buffer has a dangling reference. So the way I explain this problem to myself is that accelerator APIs have this complex zoo of types. And this zoo exists because accelerators themselves are complex hardware. But moreover, when we look at the objects that accelerator APIs have, the relationships between the objects change dynamically in the course of the application. So it's very difficult to pin down a correct relationship in terms of invariants or ownerships, because those things change. And at this point, I'll mention that OpenCL has many more types than what I've shown in this diagram, and that also this problem isn't unique to accelerator programming, but it is really painful in accelerator programming. So then what we might consider at this point is that, you start to wonder, maybe OpenCL just isn't a good starting point for a C++ abstraction. Could there be another API that we should be starting with instead? Let's look at Vulkan, which is a C API for programming GPUs. You can find out more about it here. So what I did is I put together the same graph that I showed you for OpenCL, but this time with Vulkan. And looking at what are the Vulkan objects that I need to execute a single compute shader in Vulkan. And this is the graph. So you can see that instead of being a bad starting point, OpenCL might actually be a really good starting point. Vulkan is a crazy complex. And you'll be pleased to know I won't be talking through this whole diagram. What I want to do is briefly highlight this Vulkan feature, which is the descriptor. In Vulkan, descriptors come from a pool, which means that there's a limited number of them, but also the pool kind of has ownership for the descriptors. Descriptors are used to bind parameters to shaders. So a descriptor is the way you declare what a shader's arguments are going to be when it's executed. And that makes it very difficult to figure out what the lifetime and dependencies of these various objects are, because a shader might only be valid if there are certain descriptors that are alive, but the descriptors don't belong to the shader. The descriptors belong to a pool that's independent. And the reason I'm drawing this out is because if we're thinking about creating C++ abstractions for accelerators, what we really want is an abstraction that works for many different low-level accelerator APIs. If we create an abstraction that only works for one, but isn't able to handle the complexity of a different low-level API, then we haven't really done our job well. All right, so let's summarize the key ideas from this accelerator compute section. Accelerator APIs are C APIs or C-like APIs. They tend to expose explicit resource management so that you can achieve performance with them. It's difficult to map accelerator APIs to the C++ object model because there are dynamic relationships between the objects in the accelerator APIs, and this makes it difficult to pin down what the invariants should be and what our view of ownership should be. RAII can be a liability without a clear view of ownership because we can end up with dangling references. And encapsulation hinders performance. So the way to maybe think about this a little bit is in C++, the C++ object model relies on having this memory hierarchy and virtualization to decouple interfaces and their implementations. There's really no equivalent to this when you're programming something like OpenCL. So there's no decoupling between an interface and its implementation. And the overall result of this is that it's difficult to leverage the benefits of C++, like existing code or developer know-how, when writing accelerator code. So now that I've talked a bit about programming accelerators, next off, what I would like to look at is SYCL. So SYCL is a C++ abstraction layer for programming accelerators. It was originally developed as a layer on top of OpenCL, but now it supports other low-level APIs underneath as well. The functionality of SYCL can be implemented in a C++ library, which means that SYCL looks and feels a whole lot like C++. But if you want performant applications that actually run code on an accelerator, then you need a compiler or some tooling that understands SYCL and can make some of that happen. You can find out more about SYCL here. SYCL has a large API surface, and SYCL has many ways of doing the same thing. Some of these features I really like, and I'll be honest, some of them I don't like. The reason I'm talking about SYCL here is not to tell you to use SYCL, but because SYCL has some ideas that really help think about the problems I've been describing. So that's what I will be looking at. So to get started here, I have a hello world program of SYCL, and this will compile and this will run stuff on an accelerator. Remember, the previous OpenCL example I showed you wasn't a complete program, so it needs more stuff to work. So you can already see that SYCL is much more concise than OpenCL. What's happening in this code is we create some data on the host, then we create some SYCL buffers around this data, and this gives ownership of the data to the SYCL runtime. Here I'm creating a SYCL queue and submitting what's called a command group to that queue. A command group is really a special Lambda expression. Inside the command group, I have SYCL accessors. Accessors is the way of telling SYCL that this command group requires certain buffers to work. And finally, the kernel code is in the next Lambda expression here. So this is the bit that gets executed on the accelerator. And here it's really just doing a vectorized addition. Then finally, when the SYCL buffers go out of scope, that's the point where the data that they own, the ownership of that gets returned to the user, and that's the point where the user sees the results of the kernel. So there are two features of SYCL that are relevant here that I want to draw out for us. The first of these is reference semantics. Many SYCL classes implement what SYCL calls reference semantics, and this is sometimes called a pointer to interface design pattern, or PIMPL, and another way of putting it is they behave a whole lot like a stood shared pointer in C++. The way this works is that there are small user-facing reference objects, and these are easy to move, easy to copy. They contain a pointer to some implementation object, and then they can be used to forward function calls to that implementation object. Then the SYCL runtime owns an implementation object that isn't accessible to the user. Probably this will be a reference counted implementation object, so that when all the reference objects get destroyed, the SYCL runtime is responsible for freeing the implementation object. And the benefit of this is that this approximates RAII. So it becomes easy for the user to create these reference objects, copy them, store them in stud containers, allow them to go out of scope, and so on. And then when all the references to a particular implementation object get destroyed, the SYCL runtime is able to clean up that implementation object. And what this does is it helps restore some amount of local reasoning to accelerator programming. The next feature of SYCL I want to look at is this idea of opaque interfaces. So a lot of people, when they first encounter SYCL, they assume that SYCL is a C++ wrapper around something like OpenCL. So with every OpenCL type being wrapped by a C++ class, like I showed in the previous section. And this is one possible interpretation. And I've put together a sequence diagram to kind of show what this might look like. So we can imagine the user of SYCL creating a SYCL queue. And then the SYCL runtime goes and creates an OpenCL queue. And then the user creates a SYCL buffer, so the SYCL runtime creates an OpenCL buffer. Then the user enqueues a kernel, so that's what the SYCL runtime does with the backend as well. And then the user waits for the result, so the SYCL runtime waits for the backend to finish. And there are some real implementations that are basically doing this. And I would call this the naive implementation because it's kind of the simplest one. And this isn't the only possible implementation of SYCL semantics. Next off, it's worth considering a lazy implementation. So in this case, with an implementation like this, the user might create a queue, and the SYCL runtime says, that's nice, I'm not going to do anything. Then the user creates a buffer, and the SYCL runtime doesn't do anything. The user submits a kernel to the queue, SYCL runtime doesn't do anything. And then the user decides to wait on the result. And at that point, the SYCL runtime decides that it's going to do all the work. So it'll create the OpenCL command queue, create a buffer, submit the kernel, and wait for the result. So this is a valid implementation because SYCL interfaces are opaque. The SYCL specification doesn't tell you how the SYCL runtime should be interacting with the backend that you have. And next up, we can look at a clever implementation. And this might be clever in a good sense of the word or in a bad sense of the word. So we can imagine a SYCL user creating a queue, and the SYCL runtime does nothing. The SYCL user creates a buffer, the runtime does nothing. And then the SYCL runtime wakes up and just goes and creates a command queue with the backend. The user comes in and submits a kernel, but the SYCL runtime doesn't do anything with the kernel yet. Instead, it creates a buffer on the backend. And then the SYCL runtime submits the kernel and waits for the backend to finish. And then eventually the user comes in and waits for the result from SYCL, and at that point, the work is already done, so SYCL returns the result. So again, this is quite a decoupled implementation. This is valid because SYCL interfaces are opaque. The SYCL specification doesn't tell you when things should be happening with the backend. This could be very useful because the SYCL runtime could have a much clearer view of what's happening with the backend than the SYCL user. So the SYCL runtime might be able to do clever optimizations that the user doesn't have the visibility to do. And this is also useful because some backends might not natively have the concepts that SYCL has. So you can imagine a backend that uses something other than a queue to submit work. And for a backend like this, SYCL needs to do a number of different things to approximate a queue. So we can think about the mental model that we have when we think about SYCL. So here I'm showing the user reference objects, SYCL runtime objects, and then underneath backend resources. So a lot of people will have this wrapper view of SYCL. So we have the user space objects and the implementation objects. And I would call this the bad mental model. And I would suggest a better mental model that looks like this. And you can see that this code is very similar. The only difference between this code is this bit down here. So I think it's better to think about SYCL implementation objects as optionally holding a backend resource. Right, and again, this isn't implementation advice. You shouldn't be implementing your pet SYCL implementation like this, but it's helpful to understand what SYCL is doing. It's helpful to assume that there is some decoupling between the SYCL level implementation object and whatever backend resource is being used. So then the way to think about SYCL execution looks a bit like this. And this might be, so again, this isn't an implementation advice, but this might help get people's heads around what's going on here. So the user might construct a SYCL object. This does something implementation defined in the SYCL runtime. How this interacts in the backend, we don't know. It might do something, it might do nothing. All we know is that the user gets an object with some implementation defined internals. Then this user might call a member function on this object. This will do something implementation defined in the SYCL runtime. Whether this interacts with the backend, we don't know. But what we do know is that the user has called a function with no user visible side effects. Then the user constructs a separate SYCL object. This again does something implementation defined, which may or may not interact with the backend. All we know is that the user has another object that has implementation defined internals. Then the user calls another SYCL function. Again, implementation defined behavior. There might be interactions with the backend, or there might not be. All we know is that the user called a function without visible side effects. And then finally, the user calls something like wait. Again, what this actually does is implementation defined. Whether this actually triggers interactions with the backend, we don't know. What we do know is that the SYCL specification requires that at this point, the effects become visible to the user. So whatever the sequence of function calls that the user has called produce, this is the point where these become available to the user. So the way to think about this is that by calling SYCL API functions, the user is essentially creating a sequence of actions that the SYCL runtime is required to complete. And then the SYCL runtime goes through and consumes these actions as it is appropriate and produces the required effect with the backend as it is appropriate, depending on also what the backend is. So the SYCL runtime might take these actions one at a time and produce and action them on the backend. The SYCL runtime might wait for several actions to pile up and then do them all at once. And the SYCL runtime might actually choose to reorder some actions as long as the user visible semantics of SYCL allow for that. Right, so this is all very abstract. Why is this important? This is important because SYCL has a much higher level of abstraction than the other accelerator APIs we were looking at. So that means that SYCL creates a greater disconnect between the user and the accelerator hardware. And all of this disconnect or this indirection, what this does is it creates some space where the SYCL runtime has latitude to manage the complexity of the back end on behalf of the user. And that means that SYCL has some ability to expose a more C++-like interface to the user. So if you don't think about it too much, you can kind of sort of think that what SYCL is doing is a little bit like virtual addressing and the memory hierarchy that happen in CPU code. So it's those 2 points of indirection that create a lot of flexibility between the user code and what's happening in the accelerator hardware. Now, there are some big caveats with what I've just said. The SYCL specification is large. It's not entirely internally consistent in its feature set, which means that I don't think you can implement all of SYCL the way I've described. And the second part of this is I'm not aware of anyone actually wanting to implement SYCL in the way I've described. So this really isn't about telling you to go away and use SYCL. This is about taking a few key ideas out of SYCL and showing what their value is to the problem of accelerator programming with C++. So let's summarize the key ideas from the SYCL section. We know that reference semantics help create C++-like RAII. And I've shown that opaque data types help the SYCL runtime support reasonable user-facing invariants. Invariants become a lot simpler if the user can't see what's actually going on inside the object. And by making the relationship between SYCL-level objects and backend implementation objects defined, this allows the SYCL runtime to manage the complicated ownership relationships between backend objects on behalf of the user. And we get better encapsulation because since the SYCL runtime is able to have some visibility of a number of different things that the user is doing, the SYCL runtime can potentially reorder things and do things at the same time and extract some more performance out of a backend. Okay, so now that we're done with the SYCL section, the final topic I would like to look at is SC, or safety criticality. So I put together a brief functional safety primer. When I talk about functional safety, which is shortened to FUSUM, or safety critical, which is shortened to SC, I'm kind of using these terms interchangeably. And functional safety refers to contexts where software failure can cause damage, injury, and maybe even death. And this includes things like automotive software, aerospace software, medical devices, and so on. When at C++ conference, like this one, when we talk about safeties, we often talk about the properties of languages and libraries. So things like type safety, bound safety, initialization safety, lifetime safety, and so on. Functional safety is not a language property, it's a system property. And this is because software that's executing in a vacuum doesn't cause physical harm. Software can cause physical harm when it's executing on a specific system and when that system is used in some specific way. And this means that you can write an application that uses the language that you're writing in and the libraries that you're using correctly, but the application you've written still does harmful unintended things. So remember, correctness is not composable. You can use a language correctly. That doesn't mean that your code does what you want. And the flip side of this is that an application can have its intended functionally safe behavior even if it's written in a language that doesn't have language level safeties. However, for functional safety, it's very important to eliminate software bugs, and language safeties go a long way in helping eliminate software bugs. One of the key considerations for functional safety is determinism. So that is, does the software do the same thing every time? And does the software do the same thing within the same allocated time budget every time? So this is referring to a real-time constraint, because when we're looking at real-time safety critical software, if a result is late, it might as well be incorrect. What determinism does is it gives us confidence that our software will actually behave reliably. If we develop software to be deterministic, we have some confidence that it will actually behave as intended, and we have some confidence that testing we perform on the software is representative of how the software will behave in the wild. So then when we think about functional safety in C++, just like all other software, safety critical software is made up of different components. And that means that local reasoning, like in C++, is valuable for safety critical software. So for example, if this diagram I have here represents some safety critical software application, the developer of library 1 really shouldn't need to worry about what library 4 is doing. And changing the behavior of library 1 shouldn't affect the behavior of library 4. So there's plenty of software for safety critical systems that's written in C++, and safety critical software developers often are interested in C++ because C++ has these interesting properties that help with local reasoning. But this is where the consideration of the memory hierarchy comes in. Because remember, C++ heavily benefits from there being a memory hierarchy. But this is a major source of non-determinism, because depending on where your data is at any given instant in time, that data might be very quick to access or very slow to access. And this is why every time, or just about every time you see a presentation on real-time or safety critical systems, they will talk about things like custom allocators and thread affinities, and various mitigation techniques to improve the performance determinism of their application. So there's this inevitable, unavoidable source of tension between running software quickly on a modern CPU system and running it deterministically. There are a number of compromise solutions, but ultimately it will always be some sort of compromise. So then let's summarize the key ideas from this section on functional safety. And that's determinism. For this presentation, just remember determinism. So now I've talked through these 4 different topics. And well, actually, surprise, surprise, what I didn't tell you is I have a 5th topic to talk through. The question that can come up looking at these things is there a way to combine these ideas? You know, can we program GPUs in C++ in a way that's compatible with functional safety? So what might we want from this? Well, we want to be able to program accelerators because we get good performance. We might want, and what we want is C++ style local reasoning because this helps us with productivity, this helps us with correctness, and this helps us with code reuse and libraries. But also what we want is functional safety, which has a lot to do with determinism, and specifically deterministic resource management. But now that we're introducing hardware acceleration into the equation of functional safety, the resources we care about is not just dynamic memory on a CPU. We need to start thinking about the resources of a hardware accelerator. So for example, in this diagram here, if library 1 and library 4 are using a hardware accelerator, we don't really want those libraries to have to agree with each other that they're going to be using the accelerator at a given time. And we don't want the application to need to be able to tell library 1, now you can do a thing with the accelerator, and to tell library 4, now you can do a thing with the accelerator, because that will completely destroy our local reasoning, and it will create a lot of horrible global state that is very difficult to manage. So what we want is deterministic local reasoning for accelerator resources, as well as all the other resources. So first off, we can look at the problem of determinism in space. So that is the resource footprint that our applications might have. And here it's helpful to go back to the SYCL-style pimple design pattern and look at the ways that can help in the safety-critical space. So with the SYCL pimple pattern, the application and any libraries the application might be using, they are using these reference objects. Reference objects can be stored on the stack or in fixed size containers. And the objects themselves only use host memory. So it's fairly straightforward to figure out who has responsibility for these objects. And we know that the objects don't actually own any backend resources. And that means that establishing deterministic upper bounds for the memory footprints of these objects is entirely doable. Then we can consider the implementation objects that exist in our safety-critical GPU runtime. And these could look a lot like what SYCL implementation objects look like. There might be some need for putting an upper bound into the number of these objects that can be created. I'm not entirely convinced that there is, but some variants of Vulkan do some upper bound stuff to help determinism. But again, the key here is that these implementation objects, the only resource they actually consume is host memory. And that means that we can establish an upper bound on the amount of memory they consume, and we can make the memory use deterministic. And then finally, we have the consideration of the backend resources. And what I've suggested is a SYCL mental model where these backend resources are owned optionally. And this is key. Because that means that it's up to the SYCL runtime to choose when to take ownership of a backend resource. But for backend resources, the upper bound for these is set by hardware or the low-level API, so that is fixed. But by making the usage of backend resources by the implementation object, by making that connection optional, what that means is that the number of implementation objects is no longer constrained to the number of backend resources. the number of implementation, the only thing that the number of backend resources constrains is the number of backend resources used concurrently. So this makes establishing upper bounds a lot simpler, because this basically brings back some amount of local reasoning, because it's a lot easier to establish that maybe a kernel needs at most 3 buffers for its parameters, or 10 buffers, or whatever. So in the software stack, the disconnect we have between the reference objects and the implementation objects, and then the disconnect we have between the implementation object and the resource object, it helps bring back a lot more local reasoning. And what that decoupling does is it helps us to consider each layer of the software stack somewhat independently when we're trying to figure out how much resource each layer uses, and that helps us with establishing a deterministic usage of those resources. So then this final statement just summarizes that SYCL style Pimple helps us with a separation of concerns if we want to create a safety critical GPU runtime. Next up, let's look at determinism in space. Determinism in time. And this is where the mental model I've suggested of SYCL as a sequence of actions really helps. So we can think about an application and its libraries producing a sequence of actions for a GPU runtime to consume. The application and the libraries don't need to coordinate on what sequence they're producing. All they need to do is produce the same sequence every time. So that means we don't need an application to tell a library, now you can enqueue a kernel. All we need to do is make sure that each of the components is behaving in a deterministic way. And then when we have a safety critical runtime consuming the sequence of actions, as long as the runtime consumes the sequence in the same way and it gets the same sequence every time, it can be designed to consume that sequence deterministically. And it's worth pointing out that since we're looking at an interface, we don't want to over-specify what our implementations should do. And what we need from these GPU runtimes is only to be self-consistent. If we have 2 vendors producing a GPU runtime, they don't need to be consistent with each other for us to have determinism. As long as they're self-consistent, that's enough determinism to be testable. So the point of this slide is that a view of the world where we think about accelerator programming as a sequence of actions helps us decouple the application and the libraries on the one hand, and then the GPU runtime on the other hand, and that helps us create a better view of deterministic execution. Right, so this all sounds very nice, and the question that might pop up is, is anyone actually working on this? And the answer is maybe. So the Kronos organization does have a SYCL SC working group, and they're working on a safety certifiable variant of SYCL. Now, full disclosure, I used to be involved with this working group, but earlier this year, circumstances beyond my control required me to change jobs, and that means that I'm no longer attached to this effort. Now, I need to make it very clear that this presentation is definitely not a SYCL SC working group presentation. These slides have not been reviewed by the working group, and I have no idea how the SYCL SC working group plans to address the C++ object model, and I don't know if this is even something they want to do. So I really have no idea. The reason I put together this presentation is to highlight what I think some of the value is that comes from C++, and what some of the difficulties are with programming GPUs and programming in a functionally safe way, and why I think that it is technically possible to merge these different ideas and create a safety certifiable GPU API. All right, so let's summarize the story that I presented today. The C++ object model enables local reasoning, and this is really helpful because it helps reduce bugs, it simplifies our code, and simplifies our ability to reuse code, and it improves productivity. Accelerators are programmed with APIs that are designed for explicit resource management, and accelerators have a lot of global interconnected state, which makes it very difficult to reason locally about programming them. SYCL has these ideas of reference semantics and opaque data types, which essentially raise the level of abstraction for programming accelerators. And this higher level of abstraction brings accelerator programming closer to the C++ object model. Functional safety is interested in the C++ object model because local reasoning has a lot of value to safety and correctness. But functional safety also cares about deterministic execution times and deterministic resource footprints. So what I'm arguing is that the separation of concerns that is made possible by SYCL's higher level of abstraction is aligned with the goals of functional safety. And this makes me think that a safety certifiable GPU API that interacts well with C++ should be possible, at least technically. So this takes me to the end of my presentation. If you're joining this live at Meeting C++, I will be available in the chat to answer some Q&A. Otherwise, if you made it this far, thank you for listening, and I hope you have a good rest of the day.
Thank you, Erik. That was an awesome talk. Lots of effort, and really nice to see an overview on SYCL. So then, I guess like the live audience had their questions already answered and in the chat. And if you have any questions about this, feel free to ask in the comments. And we'll go on to the break. Thank you.
Thank you.